Good morning, good afternoon, good evening, wherever you are in the world. Thank you so much for joining us today. My name is Sarah Alswalt. I will be your webinar host coming to you from Cincinnati, Ohio, here in the U.S. I'd like to welcome you to today's webinar, our topic, Enhancing Electronics Thermomechanical Analysis Workflow. And I would like to welcome and introduce our speaker today. With us, we have Robin Bornoff. Robin has been involved in the support, research, and development of the Simcenter Flowtherm product line for 25 years. As Senior Key Expert in the Mechanical Analysis Division of Mentor, he is responsible for the identification and recommendation of emerging technologies for adoption into the Flowtherm roadmap. All right, Robin, we're very excited to have you here today. I'm going to go ahead and make you presenter.
Thank you, Sarah. Let me share my screen. So welcome everyone to today's webinar on enhancing electronics thermomechanical analysis workflows. In terms of thermomechanical simulation of electronic devices, temperature date has been a good enough leading indicator of the reliability of electronic devices. It's a simple single design constraint parameter, and it's measurable. You'll find maximum rated junction or case temperature values on all data sheets for packaged semiconductor devices. And predictive thermal models are available of such devices, commonly compact thermal models, with CAE tool support to enable these models to be imported and simulated so as to predict junction or case temperature. However, temperature alone does not cause or account for failure. Commonly, it is thermomechanical failure modes and mechanisms, most commonly solder joint cracking, or often some type of package layer or PCB trace delamination. Thermomechanical simulation of the digital twin can provide insight into the mechanisms of failure to help ensure they are not designed in. In terms of the digital twin is a highly accurate model that partners the entire product lifecycle. And regardless of industry or product or process, from conception through design to manufacture and operation, the digital twin is capable of delivering greater insight, reducing development cycle times, improving efficiency, and ultimately increasing market agility. Now, Simcenter is a portfolio of products providing solutions for CAE and system simulation, physical test, design space exploration, and data and process management. And Simcenter really is central to the creation and management of the digital twin. Various physical aspects of an electronics product's behavior can be addressed with Simcenter, from thermal to structural integrity, contaminants, acoustics, onto electromagnetic performance. The Simcenter portfolio of products cover the full physics spectrum of simulation requirements. Now, I'll introduce a couple of Simcenter products and then go on to show how they can work together to provide insight into thermomechanical behavior. Let me start with Simcenter Flow EFD. Simcenter Flow EFD is a CAD-embedded CFD tool that performs thermofluid simulation. It utilizes octree meshing with a novel immersed boundary layer approach, and a wide range of industrial applications can be addressed very efficiently with this technology. Targeted primarily at design engineers, it's available on all major CAD platforms, and the robust technologies on which it is based allows for rapid and accurate CFD simulations. Simcenter 3D is a multidiscipline software that provides a wide range of dedicated solutions and pre- and post-processing capabilities for Structures, MVH, acoustics, composites, motion, rotor dynamics, durability, multiphysics, and the like. It's run in a modern CAE environment with best-in-class geometry editing and associative simulation modeling. It benefits from state-of-the-art fast and accurate solvers for FEM, BEM, multibody dynamics, fatigue, to name a few. For structural analysis, the Simcenter Nastran solver within Simcenter 3D has options such as linear, non-linear structural, modal frequency, buckling, etc., etc. It also has the ability to consider temperature load boundary conditions as an input for thermomechanical simulations. To demonstrate how Simcenter FlowEFD for NX can be tightly coupled with Simcenter 3D, a FADEC unit mounted on an engine nacelle is chosen just as a typical application example. Now, the following slides will show various capabilities of both tools, as well as how they might be employed and used together. So starting with Simcenter FlowEFD, the model building process and a thermofluid simulation will be presented first, followed by a dynamic simulation or vibration simulation in Simcenter 3D, and then followed by a combined package level thermomechanical simulation. Okay, so let's start in Simcenter FlowEFD for NX, starting with the empty chassis. It's to be populated with a PCB, and to do this, from within Simcenter FlowEFD, the EDA Bridge window is launched. The EDA Bridge window is an interfacing software that enables import of EDA data, be it PCB or package level, imported and then thermally prepared before being transferred to Simcenter FlowEFD. Let's see how that plays. So this shows how EDA Bridge can be used to import, in this case, an ODB++ layout. It's imported. Filter functionality enables thermally insignificant components to be filtered, in this case, less than, I think, 0.6 millimeters high. In terms of power dissipation, a RefDes power list can be imported. After all that's done, the modeling level of the entire PCB assembly can be defined. In this case, the PCB is represented as a lumped thermal representation. And after all those settings are made, the entire assembly is transferred into Simcenter FlowEFD. Once it's in Simcenter FlowEFD, a standard thermofluid CFD simulation is conducted. And then once the solution is complete, surface temperature plotting can indicate the thermally critical component and also other surface temperatures in the model, as well as allow the inspection of the airflows, in this case within the FADEC enclosure itself. So that's the starting point, a system-level thermofluid simulation of the entire unit within Simcenter FlowEFD. Right, at this stage, with the same model loaded in the same software environment, the Simcenter 3D pre-post interface is invoked within the same NX session. So no need to change softwares. Staying in the same environment, Simcenter 3D is toggled on. Once it's toggled on, then within Simcenter 3D, appropriate material properties are assigned, an FEA mesh is defined, and for this vibration analysis, a periodic vertical displacement profile is applied. And then a transient simulation is conducted. And from that, we can animate the transient stress distributions. In this case, just showing those distributions on the 4 brackets and then on the PCB itself. So at this stage, using the same geometry that FlowEFD used, we can identify whether the stresses are in range or the locations at which any possible strengthening or remedial design actions might be required. Okay. So having identified the thermally critical component in Simcenter FlowEFD, a more detailed thermal model of that, or in this case QFN package, can be created using another tool called Simcenter Package Creator. And then that detailed representation of the package can be transferred to Simcenter FlowEFD, replacing the original simple block model. The original block model, I suppose, is as much as you can expect from the data available from the PCB layout tool. And this will be a package outline and sometimes a height to create this lumped block representation. However, for both accurate thermal and accurate thermomechanical prediction, a more detailed definition of the internal 3D construction of the device is required. And Simcenter Package Creator is designed specifically for this purpose. It enables a parametric definition of the 3D package construction to be very quickly and easily created. And let's see how that plays. So within Simcenter Package Creator, the first thing you would do is to select your package style, in this case QFN, give it a name, define the JEDEC footprint size, number of leads, power dissipation, an assumed die size, and then the package thickness type. And then within the main tool itself, you can parametrically change, in this case, the number of leads to go from 10 to 12 on each side. The model automatically updates. Now, in this case, from a thermal perspective, we're going to exclude the bond wires from the model, assuming they're thermally insignificant. And then once the parametric construction process is complete, then this model is transferred to Simcenter FlowEFD, swapping out the original block representation that we had before. Now that we've got a highly detailed component model, for a balanced modeling approach, this necessitates a much more detailed model description of the PCB local to this detailed component. And this is defined in Simcenter EDA Bridge, where with that detailed QFN component selected, you can define a so-called thermal territory. And this is done by defining an inflation size to define the XY extent of the thermal territory surrounding the component. And then also a definition as to how far down into the PCB the thermal territory should extend, in this case all the way down to the bottom layer. The copper distribution within this volume will be represented explicitly, so an exact geometric representation for all of the conducting and dielectric objects within that volume. And then, as I said, the block representation is replaced with a detailed QFN model, and that volume of the PCB is replaced with its geometrically explicit thermal territory representation. And then those two assemblies are isolated from the rest of the system level model, so as to construct a detailed package and PCB portion model. In terms of the thermal boundary conditions for this zoomed in model, the heat transfer coefficients on the periphery of the thermal territory in the package are automatically extracted from Simcenter FlowEFD and then applied as boundary conditions on this zoom-in model. And then a transient thermal simulation is conducted, in this case a power cycling simulation with a 2-second period and 50% duty, until such time as the as the thermal responses become periodic, until such time as the package is thermally soaked to the extent where it provides a repeated periodic thermal response. Once that's achieved, then for the last cycle, so for the last 2 seconds of the transient simulation, the 3D temperature fields for every time step within that final cycle are exported. So we've clicked on temperature solid. So for each mesh cell, for each control volume in this model, the temperature at that cell at that time step will be exported for all time steps. Okay. Then again, we invoke Simcenter 3D on the same loaded model, and then start to prepare that model for a thermomechanical simulation. This involves, well, actually, first off, let me show how that plays through. So EFD is, the results are unloaded, and then Simcenter 3D is activated. Now, what we're showing here is we're going to suppress all the layers in the thermal territory apart from the top layer. There is no requirement that the structural model has exactly the same geometry as the thermal model. Any geometry that might be important for the thermal model and not for the structural model can be suppressed. Other settings to define the mechanical structural model are set, including fixing this PCB portion at the bottom 4 corner points, and then appropriate structural materials are attached in terms of the solder and the copper, etc. And then the model is meshed using a combination of quad and tet elements. Okay. Now that the FEA model settings have been completed, the 3D temperature fields that were generated by Simcenter FlowEFD are converted into a Simcenter 3D single FLD file. This is one file, a so-called table of fields file, that contains the 3D temperature fields at each time step in one file definition. Now, this single file is imported as load boundary conditions and then interpolated onto the FEA mesh and then inspected. It is, of course, going to be the case that the mesh used for the thermal simulation is not the same mesh used for the, or will be used for thermomechanical simulation. So some quite advanced interpolation technology interpolates spatially the cell center temperatures from the thermal simulation onto the nodal temperatures of the FEA mesh. And then these can be inspected just to ensure that the interpolation is correct. Not only is the 3D temperature fields interpolated in space, they can also be interpolated in time as well. So there is no requirement that the time steps used for the thermomechanical transient simulation have to match the time steps used for the thermal simulation. Once confirmation is achieved that the temperature field interpolation is acceptable, then a nonlinear transient multiphysics simulation is performed in Simcenter 3D over the same 2-second cycle period, and stress, strain, and deformation fields are predicted and inspected. So on the left, we can see the deformation of all the model. We've just hidden the encapsulant and the PCB, the FR4, for clarity. Deformation highly scaled in terms of its spatial deformation. And then on the right, we're showing the strain and stress distribution on the solder layer within the model as well, and how that changes over time. The strain and stress can be inspected. For example, we can plot a variation of stress or strain versus time for that one cycle. Actually, although not shown here, if we plotted stress against strain for this one cycle, then the area of the hysteresis loop would represent the strain energy, the energy that contributes to damage. And it's this strain energy that can be used in cycles to percentage failure prediction models, which is another value output from such a thermomechanical simulation, as well as identifying the location of which solder ball or pad in this case exhibits the biggest stress and strain. Okay. So I showed Simcenter FlowEFD working in conjunction with Simcenter 3D. Let me introduce another product from the Simcenter portfolio, Simcenter Flowtherm XT. Now, Flowtherm XT is a thermofluid CFD tool that is dedicated to electronics cooling. It utilizes the Simcenter FlowEFD mesh and solver technology, but it's implemented on a standalone CAD platform. And it has a range of very specific electronics cooling features, modeling options, and solver options, etc. Now, in terms of Simcenter Flowtherm XT being used in conjunction with Simcenter 3D, suffice to say, and without repeating the previous slides, exactly the same thermomechanical workflow can be performed using Simcenter Flowtherm XT in lieu of Simcenter FlowEFD. The only difference being that because Simcenter Flowtherm XT is based on a standalone CAD platform, all that would happen is the model would be saved out of Simcenter Flowtherm XT and simply opened in Simcenter 3D, as opposed to the toggling between FlowEFD and 3D that we saw in the previous workflow. Apart from that, exactly the same workflow and value can be achieved. Okay, for the final part, again, let me introduce another couple of Simcenter products. First of all, Simcenter Flowtherm. So Simcenter Flowtherm, very much the sister product to Simcenter Flowtherm XT. Like Flowtherm XT, Simcenter Flowtherm is dedicated to electronics cooling. It is 32 years in the market, very well established in terms of being used by thermal design engineers. It has a simple, intuitive CAD type or CAD-like interface. It's highly scalable in terms of the complexity of the assemblies, the electronic assemblies that can be considered. And then most importantly, I think for this demonstration is it is fully automatable. Yeah, and we'll come back to that. And then let me introduce HEEDS. So HEEDS, another member of the Simcenter portfolio, enables intelligent design exploration, focusing on both process automation, distributed execution, efficient search, and also insight and discovery as well. Okay, so Flowtherm and HEEDS working in conjunction with Simcenter 3D. To show how these tools work together for this thermomechanical workflow, a slightly different package level example is selected. Now, the key for this demonstration is due to the automation and scripting capabilities of both Simcenter Flowtherm and Simcenter 3D and HEEDS actually, a completely automated one-touch thermomechanical workflow can be realized. So within Simcenter 3D, this example shows a bespoke bump stress simulation dialog that has been scripted. This dialog captures the control settings for the entire one-button activated workflow. And let me just go through the various steps of that. So the first stage is this bump stress simulation dialog enables selection of a text file describing a BGA package design that itself has been extracted from Expedition Package Designer and then selected for import into Simcenter 3D. After import of this text file, a summary of the package construction is presented with the various objects' names, sizes, thicknesses, material assignments, and actually for the conducting layers within the BGA substrate, automatic extraction of the copper proportion within those layers as well. Now, the workflow includes, optionally actually, but in this case I'll demonstrate it, both the thermal and thermomechanical optimizations. And to capture the information, the settings for those optimizations, DOE count, number of computational experiments, is defined, as well as lower and upper bounds, a design space of thermal parameters, thermal conductivities in this case, and also mechanical properties as well in terms of Young's modulus and coefficient of thermal expansion. After all those settings have been captured, clicking the OK button once launches the sequentially automated flow. Now, the first thing that happens is Simcenter Flowtherm the Simcenter Flowtherm model of the package description is automatically created and solved using Flowtherm's FlowScript technology. So all of the soldables, all of the layers, the material assignments, the mesh, and the boundary conditions and power automatically scripted and defined, and then a solution instigated. And then the thermal results of this solution are saved out. So that's stage one. So that's just the thermal solution using Simcenter, Flowtherm, and FlowScript. Now the next stage is a thermal optimization. So HEEDS is then invoked in batch, so in the background. So nothing really to show in terms of its operation per se. But what HEEDS will do is it will find a thermally optimal design between the defined thermal conductivity bounds of the the level 1 and level 2 interconnect bumps. Yeah, so that automatically happens. Right, at that stage, exactly the same information, the same input deck used to create the Simcenter Flowtherm model is then used to automatically create the mechanical model in Simcenter 3D, all scripted without any manual intervention. Objects created, materials assigned, FEA mesh defined. And then in terms of the transfer of temperature information, unlike the first part of the workflow demonstration I showed, which showed a 3D temperature field or fields being transferred, here a slightly different approach is taken. Average temperatures of each individual object in the original Flowtherm simulation are extracted and set as temperature load boundary conditions on the corresponding Simcenter 3D model objects. And that temperature, object by object temperature extraction and setting on the Simcenter 3D model, again, like all other steps in this workflow, is fully automated. Once that model and the temperature load boundary conditions are defined, then the thermomechanical simulation is automatically performed, and a couple of post-processing plot views automatically created. In this case, the displacement on the left, and then the stresses on the right. And as is common for all such BGA packages, the maximum stress is on the corner soldable, and what are we? We're up at about 70 megapascals in this case. Okay, the final part is again involving HEEDS being invoked, this time in a live UI mode. And then HEEDS is used to identify an optimum set of mechanical properties so as to minimize stress and displacement within the soldables, doing multiple thermomechanical simulations with the temperature results from Flowtherm. And then the displacement results for the optimum computational experiment can be viewed. And then I think we're looking at the stress now. Yeah, again, this maximum stress again is at the corner ball, and it's gone down from 70 to about 46 megapascals. So in a one-button operation, going from an input deck to an optimized package construction, so as to minimize both operating junction temperature and stress and displacement of the thermomechanical response can be done in touch of a button. Yep. Okay, so in summary, I've presented Simcenter Flow EFD for NX, Simcenter Flowtherm XT, and Simcenter Flowtherm as well, all working in a thermomechanical workflow with Simcenter 3D. Focusing on packaged semiconductor applications, thermomechanical analysis can provide indication of solder joint stress, strain, package deformation. Probably more importantly, indication of potential failure sites in terms of maximum stress or maximum strain and displacement. And this information can help to aid design for reliability remedial actions. And then in terms of cyclic transient simulation, the predicted cyclic fatigue damage value can provide input into cycles to percentage failure prediction models. Okay, thank you very much.
And this concludes today's webinar. Thank you so much for being here, everyone, and have a great day.